Yeah, hello. Uh, am I audible? Okay. Thank you, Mathu, for confirmation. Okay. So, welcome you all. So, let's wait for a couple of minutes and we will start like within 3 or 4 minutes. So, today we will solve problem of September 2022 linear algebra. And the problems I have already sent. Later, I found that there was some typos. So, but that you could have fixed from looking at the net original problems. Okay. Yeah. So we'll wait just for 1 minute and then we'll start. So in the meanwhile, uh, I must say that there are problems on my web page uh, that you can try to solve, and that will be useful for your preparation in different examination, for example, NET, GATE, or anything. So, yeah. Yeah, before I proceed, I'll rectify one thing from the last discussion. So, in the last discussion, I told that this inner product is not a bilinear form, which was a incorrect statement. So, inner product is a bilinear form. So, this is always correct. Yeah. So, I made this mistake last time, and I later realized that that's not correct. So inner product is a bilinear form. So inner product is bilinear. That's always true. So it means that what? That if UV here, if V comma W maps to this, so this means that it is linear in both coordinates. So that is what I mean by bilinear. And inner product satisfy that property, and hence every inner product is bilinear. Okay. So, yeah, so today I plan to go a bit slower, and please stop me whenever you find some problem, or if you have some doubt, or you want to solve some problem with other methods that you already have and you want to share. So you can stop me, just uh, put some comment in the chat box, and I'll happy to share with other participants, as well as I will also learn from that. Okay, so without any further delay, let's start. So as I told, I'll be doing September 2022 problems, and there were 6 problems in part B and 8 problems in part C. No, Avirup, that is what I got the confusion in the last session. But recall that if it is on the complex thing, then it is defined as xi, yi bar. Okay, so there is a bar already on the top. So that is why I got confused, because in the last session I was not taking this bar. Okay, but in the complex, this is the inner product. Okay, so that is why I got confused in the last session, and I told wrong thing that it is not bilinear. But this is this, and this is indeed a bilinear form. Okay, so is it clear, Abiru? Okay, right. Yeah, so as I was telling, in part B, six problem was there. So it was around 18, and part C, 8. So it's 8 into 4.75. So it is like, so as I told in the last session also, that usually more than 50 marks or around 50 to 60 marks, like varies in the linear algebra. Yeah. So Avirup, it is clear, then please confirm. Okay. Okay. So let's proceed to the first problem. Yeah. So the first problem is, let A be an invertible 5 cross 5 matrix over a field F. And suppose that characteristic polynomial of A and A inverse are the same. Then which of the following is necessarily true? Okay, yeah, please. You can verify, Aviru, and let me know if you have any problem. I'll explain in the meanwhile. Okay. So, yeah, as I have already circulated you the problem sheet beforehand, so you can tell me what is the correct answer, and yeah, so you can tell me what is the correct answer of this problem. And if you haven't tried it, then we will of course try. So option A is the correct answer. So this is, yeah, right, Manmohan. So let us see why it is. So see, the correct characteristic polynomial of A and A inverse are same. So what does that mean? That the eigenvalues of A and the eigenvalues of A inverse are same. And what we know, that if lambda is an eigenvalue of A, lambda is an eigenvalue of A, right, Avirup? This implies lambda inverse is an eigenvalue of A inverse. Of course, I'm taking it non-zero thing. And since A is invertible, so therefore, like everything is non-invertible. Everything, all the eigenvalues will be non-zero. So since characteristic polynomials are same, it means that all the roots are same, and therefore lambda and lambda inverse will be same. Okay. So this implies what? This implies lambda square equals to 1, which implies lambda equals to plus minus 1. And therefore, what are the eigenvalues? Either plus 1 or minus 1. Okay. So therefore, that's why the determinant and trace we can find out. Okay. So see, determinant of a to the power 5 is 1, it is given. So that is of course not true, because if we construct the matrix, let's say minus 1, 1, 1, 1, 1. Okay, this is my A. Then this is itself the inverse. What is not correct? Manmohan? Yeah, maybe I made some mistake. You can tell. Yeah, you can tell me what I made mistake. Lambda is equals to some other lambda prime. Uh, see, when I'm saying, right, you are right. So it means that you are saying x minus 1, x minus half, x minus 3. It's like that. Uh, right. Yeah, that can happen. Yeah, that can happen. Right. You are right. That may be possible. But yeah, but yeah, I need to check once that you are right that theoretically that's possible, that if lambda is there and lambda inverse is there. So it may happen that, suppose that lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, then it may happen that this is equals to lambda 2 and this is equals to lambda 1, this is lambda 4, this is lambda 5, and this is lambda 1. It may happen, right? Yeah. Yeah, but still, see, still you can see that the eigenvalue of A will be either plus 1 or minus 1. 1 lambda, lambda square, lambda cube, lambda to the 4. Right, that is true, and you are assuming uh, lambda is the fifth root of unity, right? Right, you are right. Yeah, you are right. That is true. That I can just take 1 xi square, xi cube, xi to the 4, right? And here the inverse is basically xi inverse is xi to the 4, xi square inverse is xi to the 3. Right, you are right, Manmohan. Yeah, yeah. So I take my word back. Yes. So yeah, but if I take this example, right? But if there is minus 1, then another minus 1 is there. Why? Why you are saying, Matho, that if there is minus 1, then there is another minus 1? For example, if I take A as this matrix, this is invertible, and the characteristic polynomial of A and A inverse, which is same here. So A inverse is what? What will be the A inverse here? So it's minus 1, 1, 1, 1, 1. This is the A inverse. Yeah. So this is this. So yeah, this is the A and A inverse, and the characteristic and the polynomials are same. So, but what is the determinant of what is A square? So A square is the identity matrix. So therefore, the determinant of A square is 1. Determinant of A to the power 5 is equals to 1. That's not correct, because if I take A to the power 5, there is 1 minus 1 will be here, and therefore you will be getting minus 1 in the determinant. So this is not correct. Similarly, trace of A square is 5 here, so that's not correct. And trace of A to the power 5 is 1, that is also not correct. And therefore, this option is correct. Okay. So the product of the determinant. So basically here, see. So Matho, is it clear now? You are telling that if there is minus 1, then another minus 1 will be there. But that's not true, because you see, I've given an example. This is A and this is your A inverse. No, but what is, see, A I have taken at what? 0, minus 1, 1, 1, 1, 1, 0. If I'll do it square, what will be, if I'll do it square of this matrix? This is a diagonal matrix. If I'll do the square of this, what will be this? If I'll do the square of this. Square of this is nothing but 1, 1, 1, 1, 1. Because this is a diagonal matrix. And hence A square will be 1, 1, 1, 1, 1, 1. Okay? Yeah. Yeah, of course. See, in that example, see, in general, I'm not saying that it is the A square is an identity matrix. That's not true. Of course, in general, that's not true. But what I'm saying in this example, if I have constructed this example A as this, then A square is identity for just for this example. Okay, and therefore I have, it's not in general I'm saying just for this example, uh, A square is identity, and which will discard the option 2, 3, and 4. And that's why these three are false. Okay. So is this clear to everyone? Then I'll proceed to the next problem. Okay. Yeah, Manan, thanks. Okay. So this was an easy problem. So again, see, in the last session also, I emphasize on the two properties, and again we are using the two properties, that sum of the eigenvalues is equals to the trace, and product of the eigenvalues is equals to the determinant. As I told in the last session also, that these two properties are Very important. Yeah, but why option one is correct, that we have not discussed. Yeah, right. So yes, right. You are right that we have not discussed. So and I also haven't thought about that. So if you have any thought, you can tell that. Yeah, this week I didn't get much time to solve every problem. So if you have, like, if you thought about that, we can say, as you told. Yeah. So can you say, Manmohan, why option one is correct? Of course, uh, 2, 3, and 4 is this, and there will be determinant of A and A inverse are same, right? So determinant of A is equals to the determinant of A inverse. Why? Because of the eigenvalues are same, and hence the product of the eigenvalues will be same, and hence the determinant of A and determinant of A inverse is same. And what does that mean? Determinant of A is equals to 1 by determinant of. So this means, so I'll just write this in one line. Yeah. So this means, so determinant of A inverse is 1 by determinant of A. So this means determinant of A square is equals to. So that will give me determinant of A whole square equals to 1. Okay. And here we need to prove determinant of A square is 1. Okay. So this equation, that determinant of A and determinant of A inverse are same because product of eigenvalues in any order are equal. Right. Yes, you are right, Manmohan. So if, as I told, if lambda 1, lambda 2, lambda 3, dot dot lambda 5 are the eigenvalues, then of course the eigenvalues of A inverse, we know it's like 1 by lambda. It may not be lambda 1, lambda 2, but let's write it 1 by lambda 1, 1 by lambda 2, 1 by lambda 3, 1 by lambda 4, and 1 by lambda 5. So the product is, it's like, so the product of lambda I and the product of 1 by lambda I will be same. Okay. So therefore, the if you take the square of that, so what will happen? Square. If you take the square, then I know that the product of the eigenvalues of A and eigenvalues of A square gives you 1, and therefore if you take the eigenvalues of A square and take the product, that will again give you 1. Yeah, yes, that's right. But no, then we multiply determinant both sides. See, the thing is, no, that's not. See, Manmohan, determinant of A equals to determinant of A inverse. If you multiply determinant of A both side, determinant of A, so this will give me 1, but this will give me determinant of A square. Okay, this will give me determinant of A square, and which is not same as determinant of A. Oh, right. Determinant of A square is same as, right. Yeah, you are right. Yeah, this is the property. Yes, which is same as determinant of A square, right? Because determinant is multiplicative, right? Yeah, you are right, Manmohan. Yes. Thank you for the help. Yeah. So let me just summarize this. So because it may not be clear to others, so let me just quickly summarize this. So the first thing is that characteristic polynomial of A equals to the characteristic polynomial of A inverse. This implies the product of eigenvalues of A is same as product of eigenvalues of A inverse. Okay. So this implies determinant of A is same as determinant of A inverse. Okay. And this implies determinant of A inverse, or let me write determinant of A times determinant of A, which is equals to determinant of A times determinant of A inverse. Now determinant has this property that determinant of A times determinant of B is same as determinant of A times B. Okay. And therefore this implies that determinant of A square, which is same as determinant of A square, which is equals to determinant of identity, which is equals to 1. So determinant of A square equals to 1. Okay. So I hope this is clear. And thanks, Manmohan, for helping me out. Okay. So if any problem, please let me know. I will proceed to the next problem. Yeah. So yes. So suppose A and B are real similar matrices. That is, there exists an invertible matrix S such that A equals to SB S inverse. Then which of the following need not be true? Okay. So yeah. So any thought about this problem? So A and B are two similar matrices, and we have to talk about what about the transpose, minimal polynomials, trace. Yeah, so option C. Option C means trace of A equals to trace of B. So you are saying that this option. Okay, let's see. We'll see this. What about other? So this is, I guess, this option is by Khalid. Okay, so this is by Khalid. Okay. Manmohan is also saying C. So you are saying the trace of A need not be equal to the trace of B. Okay. Let's see. Okay. So let's see. See, A and B are similar matrices. Okay. So let's see what is the relation between, because if we can see what is the relation between eigenvalues of A and B, then we are done. Okay. Then we can say about the trace. So let's talk about the option 3 only first. So option 3, let's see. So let's say let V is an eigenvector, okay, of A. So this implies, and let's say eigenvalue lambda. So this implies what? AV equals to lambda V. Okay. So from this, A I know is SBS inverse. So let's write SBS inverse V is equals to lambda V. Okay. So from this, what can I say? I can just multiply S inverse both sides. So S inverse S inverse V equals to S inverse lambda V. And this is equals to B times S inverse V equals to lambda times S inverse V. Okay. Now since V is a non-zero vector and S is an invertible matrix, so this is a non-zero thing, and this implies that lambda is an eigenvalue of B with eigenvector S inverse V. Okay. So then what can we say about this the trace? Then what can we say about the trace? Now what is the thing about the trace? If now we know that all the eigenvalues of A and B are same. So if A and B are similar matrix, if A and B are similar, which implies eigenvalues are same. Are same. Okay. So what was the thing? Which of the following need not be true? So then trace of A is equals to trace of B. Then this option. So this is correct option. I mean this is true. This is not. So this is true. This is true. Okay. So Khalid and Manmohan, is it clear? Option 4. Yes, right. We will see that also, right? So yeah, Swarup, you are right that option 4 is the correct answer. So Manmohan and Khalid, is it clear that this is the trace of A and trace of B is always correct? Okay, yeah, okay. And you see, if option 2 is correct, that if what is the option 2? It says that minimal polynomials of A is same as the minimal polynomial of B. It means what? If option 2 is, if you are saying that option 2 is false, it means that this is true. So this means that already that eigenvalues are same and hence the trace will be same. So this option is, so this is true. Let's talk about what about 1 and 2. Okay, so let's see. And so in this way we can see what are the properties of the similar matrices also. So first see what about the transpose. So A equals to S B S inverse. So if I take the transpose, then A transpose equals to S B S inverse transpose. And what is the transpose of AB? It's B transpose A transpose. And therefore this I can write S inverse transpose B transpose S transpose. And that's why this says that A transpose is similar to B transpose. Okay. So this proves that A transpose and B transpose are also similar. Okay. Right. And the minimal polynomial of A is same as the minimal polynomial of B. So this also you can see, like, see, if summation of A n x to the power n, if this is the minimal polynomial, okay, so you see that all the polynomials, so I am saying my claim is, if f of A is equals to 0, if and only f of B equals to 0. Okay, so this will, in particular, this the last claim will in particular prove that the minimal polynomial will also be same. But this is easy because if this is my f, then what is f of s, or what is a? F of A? It's same as f of s b s inverse. Okay, but what is this? This is summation a n S B S inverse to the power n, where n is running from 0 to uh, let's say 0 to L. Okay, fine. So now you see, so what can we talk about this? If I take the powers of this, so what is this? So if I take S B S inverse square, so what is this? This is my S B S inverse times S B S inverse, and this will go, and this is equals to S B square S inverse. So what is this? So this is this quantity is equals to S B to the power n S inverse. Okay, and therefore what we can write, that this is equals to summation a n S B to the n S inverse. And now I can just take this S outside the summation. This is a n and this is B to the n and then S inverse. Okay, so you see that if f of A equals to 0, if this is equals to 0, then this is will also be equals to 0, and S is an invertible matrix, which implies summation a n b to the power n is also 0. So this says that whatever polynomial A satisfies, B must satisfy the same polynomial. And this in particular proves that if A and B are similar matrices, then, so this proves that their characteristic polynomial are same. So characteristic polynomial same, minimal polynomial same, okay, and hence determinant, trace are also same. Okay, okay, and that means if A is diagonalizable, if and only B is diagonalizable, all the properties which are related to this are true. Okay, and therefore this is true, this is also true, and this is also true. And hence this has to be false, but let's see an example. What is an example? So I'll take A equals to 1, 0, 0, 0, and B equals to, I guess, 0, 0, 0, 1. I guess this is the thing that I took. Yeah. So A and B are similar matrices, but what is the range of A? Range of A will be x0. Okay, it is spanned by this thing, so that X is in R, and range of B is equals to 0x, so that X is in R. Okay, and of course, so see, 1 comma 0 is in, so transpose 1 is, this is in the range of A, but this is not in the range of B, so they are not same. Okay, so this problem is clear to everyone. Then if you have any problem, we can ask now, and then we'll proceed to the next problem. Okay, so fine. So let's proceed to the next problem. And whenever you have problem, just stop me in between. I'll try to rectify that. Yeah. So the next problem is, suppose A is a real n cross n matrix of rank R, and let V be the, so this is the, yeah. If V be the vector space of all real n cross n matrix X such that Ax equals to 0, then what is the dimension of V? Yeah. So any thought about this problem? What could be the correct answer? Any thought? B. So Khalid is saying B. This is Khalid. And Surya and Sujata are saying this. So this is Surya, Sujata, Abhirup, and yeah. Could you explain given any how to check? See, as I told, they are similar. If and only, so that is the thing, that they are A and B are similar. If you can find an S such that A equals to S, B, S inverse. I don't know whether if there exists any uh, algorithm to check whether they are similar. So yeah, I don't know whether there is any algorithm. Yeah, if I came, I'll try to see if I came to know that if there exists any. Yeah, of course this finding S. But see, uh, of course this finding S is a difficult task in general. Of course that you are right. So I'll try to see that if uh, yeah. So I'll try to see if there is any condition as such. I don't know. Uh, Honestly, I don't know. So yeah, if I find any condition, or if you guys know any condition, then you can say here. Okay, option 4. Yeah. So option 4. Right. So yeah, so it seems then option 4 is correct because majority of the vote goes to. So let's see why. So yeah, so what it says that if A is a real n cross n matrix, so what I'll do, what is V? V is the set of all X in M and R such that Ax equals to 0. Okay, yeah. So what I will do, I'll define a map phi A from MNR to MNR so that I can see V as the kernel or the rank or something, so so it will be easier for me to attack on the space V. So I'll just define as usual, X goes to AX. Okay. Then what is kernel of phi A? This is precisely your V. Okay. So finding the dimension of V is same as nullity of phi A. Okay. So yeah, there may be many like methods to solve. So how I solved it. So I'll try to write down the matrix of phi A. Okay. So let's see just for the and like visualization. See if A is equals to, let's see, A, B, C, D. Okay. Let's just act on 2 cross 2 matrix. If A is equals to this, then what will happen? What is so I'll take the basis of V or basis of MNR, because instead, in order to find out what is the what is the matrix of linear transform, I have to fix a basis. So I fix an ordered basis. So I'll fix a basis of MNR at this 1 0 0 0 0 0 1 0 0 1 0 0 and 0 0 0 1. Okay, so this is an ordered basis I have fixed. Okay. So this is E11, this is E1 is 21, this is E12, and this is E22. So what if I add phi A of E11? What is this? I'll be getting A, C, so A, C and 0, 0. Okay. And what is phi A of E21? So this is A times E11 plus C times E21 plus 0 plus 0. Okay. And if you find out E21, so what we will be getting? Since it's there, so you'll be getting B, D, or let me just see. So A will be coming B, and this is, since we are in the second thing, so this will survive. So your BT and 0, 0. Okay. And this is equals to B times E11 plus D times E21 plus 0, 0. Similarly, phi A of E 1, 2 will be what? What will be this? It's a 0, 0, and the next will be what? It's nothing but AC. Okay, so this is 0, 0, AC, and finally, if you find out phi of E1, E22, you'll be getting 0, 0, BD, which is equals to 0, 0, BD. Okay, so what is the matrix of this linear transformation? So it is A, C, 0, 0, B, D, 0, 0, 0, 0, AC, and 0, 0, BD. So this is nothing but A, 0, 0. Okay. So if you choose the basis as I have chosen, so if you choose the basis as, if I'll choose my basis is equals to Eij as the column thing, okay, like firstly I'll vary I and then J as a column wise, then the matrix corresponding to the phi A will be A, A, A. Okay, this will, and this is 0, 0. So what is the rank of phi A? So rank of phi A is equals to rank of A times N, total size. Okay, and this is nothing but N times R. Okay, so the rank of phi A is N times R, and therefore I'll use the rank nullity theorem. So nullity of phi A is equals to N square minus NR, and this is the dimension of V. Okay, so is this clear to everyone? Yeah. Okay, so I hope it is clear. So if you have any doubt, just let me know. We'll proceed to the next problem. Okay, yeah. So I guess this problem was not added before, but when I was checking the problems again, then I saw that this was also a problem from linear algebra. When I saw in the beginning, I thought it's AN, so I thought it's from real analysis, but later, I guess some of you told that this is also a problem, and this is R, real R, not ring R. Yeah. Okay. So, right. So let us define a sequence AN of real numbers to be a Fibonacci-like sequence if it's a Fibonacci, so if it satisfies the Fibonacci thing for all n greater than equal to 3, then what is the dimension of the R vector space of Fibonacci? So So what is V? So V is my an such that an equals to an minus 1 plus an minus 2 for n greater than equals to 3. Okay, so this is a vector space. We can check that. It's not a difficult thing. And hence, we need to find out what is the dimension of each what. Okay. So any thought about this problem? Yeah, dimension is equals to 2, Swaroop, right? Yeah. Any other guesses? Yeah, Sujata, right? So this is clear. So because an is determined by the first two choices. So once we fix the two choice, like so if I have, let's say, the first, if I have like a1, a2, then this will be a1 plus a2. This will be what? It's like a2 plus a1 plus a2. It's like this. Okay. So it means that if I fix this, then all of them will be fixed. Okay. And therefore, what is the dimension will be 2. So the dimension will be 2. Okay. Fine. So the dimension is 2. Right. So this is clear. I hope this was an easy problem. Yeah. Let's proceed to the next one. Problem 5. Let R be the field of real numbers and let V be the vector space of all real polynomials of degree at most 1. So it means that V will be something AX plus B such that A and B are real numbers. Okay, this is my V. Dimension of V is 2. Now consider the bilinear form defined as this. Okay, and we need to see for which of the option is true. So yeah, any thought about this problem? That which of them will be true? Then I'll proceed. Yeah, any thought that which of the which is the correct option? Okay, so yeah, let me do that. It's not difficult. Yeah, I'll just make a here two correct answers I'm getting. Okay, option 1 and 3. Okay, let's see. 1 and 3. Yeah, I got option 3. Okay, we'll check. I got only option 3. So we'll see that. Yeah, and I'll make a suggestion here that see, uh, in order to qualify the exam or to get a good rank in the CSIR net, I suggest you to solve the problems. Okay, because if I'll solve the problems, you'll not get much benefited. So I suggest you all that whenever I this time I was late in sending the problems, and but you have the problems from the internet. So before coming to the session, I recommend you all to solve the problems so that you will get most out of this session. Okay. Otherwise, it's just like coming and sitting the session and like it won't help you much. That's the thing. Okay. So let's see. Yeah. So what is the first option? So first option is for all non-zero real numbers AB, there exists a real number C such that vector AX plus B and X plus C are orthogonal. So what do I mean by orthogonal? So orthogonal means V and W are orthogonal if inner product of V and W is 0. Yeah, I sent the problem in the on the WhatsApp group before. And since these are the previous year problems, so you can solve it like from some like, of course, the problems will be available somewhere online. Okay, but anyway, I usually send like in the last time I sent in problem 3 y rank of. Y is rank A times rank A, where n is coming into the picture again. Yeah, I'll do that one more. Let me first solve this and then I'll come back to that. Okay. So yeah. So let R be the field. Yes, sir. So let's see. So we need to see when VW is equals to 0. So let's see the first option. So it says that the inner product of AX plus B and X plus C is 0. So let's see. It means that from 0 to 1, if I'll do AX plus B times X plus C, I should get 0. But what is this? It is 0 to 1 AX square plus AXC plus BX plus BC is equals to 0. Okay. And this is equals to what? 0 to 1 AX cube by 3 plus AC plus B x square by 2 plus BCX and sorry, oh, I integrate it. And when you put the 0, 1, you will be getting A by 3 plus AC plus B by 2 and plus BC. And this you want to be 0. Okay. Now A and B are fixed. So A and B are given. A and B are given. Okay. What we need to determine C, because it is what this question asks you, that given A and B, can you find a number C? So it means that I have given you A and B and you need to find out what is the number C. So let's see if we can solve C always. So this is A by 3 plus AC by 2 plus BC plus B by 2. Okay. So this implies, so this is equals to 0. So let's write equation. Yeah. So this means A by 3, or if I take C as common, so A by 2 plus B is equals to minus A by 3 minus B by 2. Okay. Now, see, A and B can be anything because it says that for every A and B. So what I will do, I'll choose A as 1 and B as minus half. So then what will happen? This will become 0. The left side will become 0 and this will be non-zero. And hence this equation you cannot solve it. Okay. So therefore, for every A and B, you cannot find C such that the given two vectors are orthogonal. Okay, and therefore option 1 is not correct. So this is not correct. B is minus half. Oh, right, yeah, you are right. Yes, B is minus half, right. Okay, yes. Okay, so right. Let's talk about the option B. Option 2 is X plus B, X plus C. So I'll just check this one, and rest of them are, it's like you can just, of course, you can just directly do the inner product of AX plus B and that C and then find out direct condition. Okay, so that's not difficult. So the second option is X plus B and X plus C. So let's quickly do it. X plus B, X plus C, and it says that for all numbers B non-zero, there are infinitely many C. Okay, so let's see. 0 to 1, so this is equals to X square plus B plus CX plus BC. And when you do integration, so this will be X to the 3, so that's 1 by 3 plus B plus C by 2 plus BC equals to 0. Okay, now again the same problem, like given B, can you find infinitely many C? Okay, so this implies C by 2 plus BC equals to 1 by 3 plus B by 2 with negative sign. Okay, so this implies C equals to 1 by 2 plus B equals to this thing. Okay, again the same scenario is there. You can choose B equals to minus half, and then even you don't have a solution, forget about infinitely. Okay, so this is also not correct. And now it says that for all positive numbers C, there exist infinitely many real numbers A and B such that all the vectors AX plus B and X plus C are orthogonal to each other. Okay, so let's see this. So now it says that C is fixed. Okay, so now this C is fixed, and we have to see that can we always find A and B and not one. It's like infinitely many real numbers such that these two are orthogonal. So let's see this. Okay, so let's see. So ax plus b and x plus c, 0 to 1. So what is this? As I told, you can directly take ax plus b, cx plus d and solve it and get whatever the condition that you need. Okay, so this will be ax square plus b plus ac times x and plus bc. And if you integrate, you'll be getting a by 3 plus b plus ac by 2 plus bc. And this is equals to 0. And this implies a by 3 plus b by 2 plus AC by 2 plus BC equals to 0. So this implies what? A by 3 plus B by 2 plus, if I take C as common, then A by 2 plus B is equals to 0. Okay. But now you see that C is given. Okay. And A and B that you need to choose. Okay. So so I need to solve this equation for A and B. Okay, so this is one equation and two unknowns because A and B both are unknowns. Okay, and of course you can solve for infinitely many solutions. Okay, so that's not difficult because the coefficient of A is 1 by 3 plus C by 2 plus B is 1 by 2 plus C, this and this is equal to 0. And this is just a linear equation in A and B, and that has infinitely many solutions. Okay, so this is correct option. Okay, and now for all non-zero real number B, there are infinitely many real number C, so that the vectors B and x plus C is in V, so that you can check. It's a similar calculation, so I'll leave it to you to check. This is not correct. Okay, okay. So let's go to the previous problem where I discuss, yeah, this one. So see the rank, the what was the A is from MNR here, okay, and rank of A is equals to R, okay. So A will be what? A will be, I can, like, after doing the this the what is that called? The elimination thing. I can just write A as like the first row, second row, third row, rth row, and then 0. Okay, so is this. So now just see in just two things. Just see in the 2 cross 2 blocks. So what is this? So if I write this, I'll be getting V1. This is, let me make V2 dot 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 VR and then 0 0 0. And from n onwards, so this is my this, and from n onwards, I'll be getting V1, V2, V3 dot dot VR and then 0. So how many? See, these are already linearly independent, and these are also linearly independent. And since here we'll be getting 0, and here it's 0, so as a whole, this and this will be linearly independent. Echelon form, right? Right, yeah, right, yeah. Echelon form. So if I then VR, and then you'll be getting 2 times R. Okay, so if it is n, the size of the matrix is n, so you'll be getting a n times here, and that will give me R, and that will give me n times R as the rank of this matrix. Okay, is it clear, Manmohan? Okay, so let's proceed to the next problem. This one. Yeah, okay. So let A be a real symmetric 3 cross 3 matrix. So it's a symmetric matrix, and consider the quadratic form this. And then we have to see that if Q is quadratic, then how it is related to the matrix A. Okay, okay. So recall that quadratic form positive definite means, so Q is positive definite. It means what? It means that for every x non-zero, that Q of x is greater than 0. This is what the meaning of Q being positive definite. Okay, so See, but can you see that Q is positive definite implies A is positive definite? Q is positive definite implies A is positive definite. Okay, so Q is positive definite because this is what? This is nothing but like X transpose AX. So because this matrix A X transpose X. So if this is your positive definite, if Q is positive definite, then this must be positive definite. Otherwise, of course, may not be true. That it may happen that this is positive definite, but Q may not be positive definite. We will see that. Uh, sorry, I made a mistake. Sorry, Ah, sorry, that's not correct. What I told. Yeah, Q is positive definite. This is if and only if A is positive definite. Yeah. So Q, the quadratic form, Q is positive definite if and only if the matrix corresponding to A will be positive definite. Okay. So let us see when does a symmetric matrix is positive definite. Okay. So any thought about when does the symmetric matrix is positive definite? Any thought? When I say that a symmetric matrix is positive definite, okay, let's see. So see, A is symmetric, A is symmetric, all leading principal minors are positive. Yeah, but like you can like say it even much more simpler thing. It's like see, A is symmetric. This implies I'm saying A is equals to greater than symmetric positive definite, of course, positive definite. If A is symmetric and positive definite, then all the diagonal entries must be bigger than zero. Let's prove this. This is not a very hard proof. Right. All eigenvalues are positive. Yeah, of course, all the eigenvalues are positive. That is by definition. Like that's not by definition. That can be proved from X transpose AX is greater than zero. This implies all the lambda are greater than zero. All the eigenvalues are positive. Of course, right. But since see in the option we need to see in AII, 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 AII. Okay. Okay, and that is true in general, not even symmetric matrices. See, even any matrix, if for any matrix A, if it is positive definite, this implies that lambda is greater than zero. That is true for every matrix. Now you are given with symmetric matrix, some special matrix. So what is the extra property that you will be gaining? Because now you are having some extra property that is a symmetric matrix. So if it is a symmetric matrix, so it means that all the diagonal entries will be greater than zero. Why? So let's see. So if you have, you can prove it in general. I'll just show you in 3 cross 3 and the, just the proof will be literally same. There will be nothing else. A13, A12, A22, A23, A13, A23, A33. Okay. Okay. So this is my A. Okay. So if this is positive definite, it means that if I act X transpose AX, yeah, of course we can take it, but I'm saying that all those things is not needed. It's just, of course, you can take the Jordan form. Yes, so AX transpose AX is greater than zero for every X. Okay, I'll take A, X I'll take as 1 0 0, then I'll take 0 1 0, and finally I'll take 1 0 0 1. Okay, I'll just take these three things. And then what is X transpose AX? If you do with this thing, you will be getting A11. If you do this thing, you will be getting, so let's name it E1, E2, E3, and if it is my E1 transpose A E1 is A11, E2 transpose A E2 is A22, and E3 transpose A E3 is equals to A3. Okay, greater than 0, greater than 0, greater than 0. So all the diagonal elements will be greater than 0. And hence Q positive definite implies A I is greater than 0 for all I. Okay, got it? Okay, fine. Now, so this implies that, mm, yeah, so this implies that this option is correct. Now, what about other options? Other options are easy to check. I'll just see why this is not correct. See, this is just the converse of the above one, that if A11 is greater than 0, then Q is positive definite. That need not be true, because if I'll just construct this matrix 1, 1, 1, oh, this is for 3 cross 3 only. Okay, then fine. You don't have to go for arbitrary. 1, 1, 1, 1, 1, 1. If I construct this matrix as A, okay, this is my A. Clearly, all the diagonal entries are greater than 0. This is a symmetric matrix, but this is not positive definite, because the determinant of this is 0, and hence one of the eigenvalues is 0, and therefore this is not a positive definite matrix. Okay, okay, so done. So this option is false. Okay, got it. Yes, right. 0 is an eigenvalue, right? So yeah, so this completes the part B. So I'll just uh, um, take a pause for 3 to 4 minutes, and if you have any problems, we can discuss it now. Then I'll proceed to the part C. Yeah, so what do you think? Like, how is the pace going on? And like, is it fine, the pace? Yeah. Yeah, you can comment. Yeah, like, how is the pace? Like, is the pace is fine? Okay, right. Okay. Yeah, I will just give 2 minutes break, and then we'll start again, part C. It has only three options and one and I don't know. Oh, I guess I made some mistake here. Okay. Yeah, right, Manmohan. We can take a break on every hour. That's not a problem, because then everybody will be fresh, and then that will be better, that you will be learn more. And feel free to interrupt me. Like, uh, you are talking about the last problem. This the positive definite problem. Oh, acha, in part C. Okay, okay. Oh, yeah, maybe now I do not have the problem, because so I don't know what was the options. But let's see, like, whatever the options we have, we will just analyze those things. So, okay. Yeah, I hope we can start now. So it's already 5 minutes. So yeah, right. So yeah. So the problem is, let A be an n cross n matrix with entries in R. So it's MNR. So A is in MNR, real matrices, such that A and A square are of the same rank. Okay. and consider the linear transformation T from Rn to Rn defined by Tv is equals to AV, then which of the following are true? So we need to talk about the kernel of T and T compose T. So another option is A must be invertible. Okay, so let's add that. Option 4 is A must be invertible. Yeah, right. Okay. So let's start with this option only. So this option is of course false because I'll take A as zero matrix. Then because nowhere it is mentioned that it's a non-zero matrix. So I'll take A as zero matrix. Then A and A square are same and hence have the same rank. And therefore this option is false. Yeah. So yeah, any guess about the other options? One, two, three. Yeah, any guess? Three is false. Okay, so this is also false. Okay. And what about option one and two? Yeah, if one is true, then of course two is true. Because if the kernels are same, then of course the dimension would be same. So take the diagonal minus 1, 0, 0 for option 3. Right. Yeah. So let's see. So the option 3 as suggested, I'll just 2 cross 2 matrix is fine. So minus 1, 0, 0, 0. So if I will take A as this, then what is A square? It's 1, 0, 0, 0. Both have the same rank. Okay. But an eigenvalue of A is minus 1 and therefore In plus 1 will not be invertible. So I'll just write because this is also sometimes important that In plus lambda A is invertible if and only if 1 by lambda is or minus 1 by lambda rather minus 1 by lambda is not an eigenvalue of A. And this is very easy to prove, so I'll leave. So you can just try. So this is not difficult to prove. Okay, so hence, so the eigenvalue of A is minus 1. This will work. A. Because rank of A and rank of A square are same. Because what is the rank of A? It will be like x comma 0. It's minus x. And A square will also be my x comma 0, where x is a real number. So what won't work, Manmohan? Oh, acha, A must be invertible. Oh, acha. No, I have option. Oh, I have written both options, but I have combined this. Okay, okay. Yeah. No, what will not work, Manmohan? Could you tell? This option, this A will work, I guess, because In plus A, of course, is not invertible, and A and A square have the same rank. It's 1. Oh, no, yeah, that's why I just realized that this is a full stop, and since this option, I guess Sujata told, yeah, so that's right. And since this was an option, right? Yeah, so this is option 3, and this was the next option. Yeah, fine. Yeah, I made it. Right. Okay, let's see, what about the kernel and even range also we can talk about. Rank is same. So let's see. So A and A square, there are two matrices. Okay. Let's see. Uh, what can we say if C? Okay. If V is in the kernel, so if AV equals to 0, this implies A square V equals to 0. This is, if AV equals to 0, then A square V is 0. So this implies that kernel of A is contained in kernel of A square. Okay, okay. So keep this thing. And now let's talk about the range of a and a square. So a and a square. So if w is in the range of a square, this implies that there exists some v such that a square v is equals to w. But this means that a of av equals to w, and this means that w is in the range of a. And therefore, what can I say? That range of a square is contained in range of a. Okay, yeah. So range of a square is contained in range of a, and this is a vector space, and this is also a vector space. And if you have two vector space v and w, and one is contained in other, and dimension is same, you both have the same dimension, then this implies that v equals to w. Okay, so here, since the rank of a and a square is the same, so it means that these two are same. And similarly, rank will be same, it means that the kernel will be same, the nullity will be same, and hence the kernel will also be same by the same logic. Okay, and therefore these two options are true. So this is in general fact is like the range of a square is contained in range of a, and kernel of a is contained in kernel of a square. And this is true, like, so it's like a cube, a4, it's like r of a5, all containment are true, and the opposite containment will be true for the kernel. Okay, so, and this is the thing that if you have two vector space, one is contained in other, and then the dimensions are same, then the two vector space will be same. Okay, so this is clear, I guess. So any doubt, you can stop me. Okay, so we can, right, so we can proceed to the next problem. Yeah, so the next problem is for a positive integer n. I could not follow. Can you please repeat? Okay, I'll repeat down. That's not a issue. So let's add a page here and then we'll add. See, what is given here? Rank of a is equals to rank of a square. And what we have, what we showed is like a range of a contains the range of a square. And we also saw that kernel of a is contained in kernel of a square. Okay, these two things are clear, Manmohan, now? Okay, so see, rank of a is same as rank of a square, implied if I'll apply the rank nullity theorem, this implies that nullity of a or nullity of a is equals to nullity of a square. Okay, and now you see that you have this vector space, because this is a vector space and this is again a vector space, and one is contained in other, and the dimension is same, both have the same dimension. Okay, so it means that what? This vector space is same as this. So if V is contained in W and dimension of V is equal to dimension of W, this implies V equals to W. And how do you prove that? That's not difficult. See, V is contained in W and dimension of V is equal to dimension of W. So what I will do, I'll choose a basis for V. V1 to Vn. Okay. And since the dimension of V and dimension, since V is contained in W, so this all elements will be contained in, and so V1 or Vn all are in W. And since they are linearly independent because they are the basis, and hence they will also be linearly independent here. And n linearly independent element you got, and that's a maximal linearly independent because the dimension is n. and therefore this will also form a basis of W. And this will prove that these two spaces are same. Okay, and hence this range of A square is range of A and kernel of A square is kernel of A. And now you have everything. Okay, so is it clear now, Manmohan? Okay, yeah, right. Okay, so we can proceed to the next problem. Yeah, I can see that there is a slight lagging between me and the online thing. So yeah, I don't know that that's a problem of, I guess, YouTube or something else. I don't know. So let's see this problem. So for a positive integer n, let M and R denote the vector space of n cross n matrices with entries in R. Okay, so it's just M and R, and which of the following statements are true? So yeah, so any thought about this problem? Yeah, any thought? What would be the clear? What would be the right answer? Which of the following are true? Yes. Yeah. Any guess? Okay, so let's try. So okay, fine. So the let's try with the first option. What is the first option? The vector space M and R can be expressed as the union of a finite collection of its proper subspace. Okay, so can it be true? See, it's a union of finite collection. So here it's union. Okay, okay. So can it be true? So see, if is it true for any vector space? Two is true. So two is true. Yeah, that's true, right, Avirup? And one is true, Manmohan. You're telling. Okay, let's see. But Manmohan, I'm telling that this is not true for any vector space. Forget about M and R. Why? So let's see why. Of course, I'm taking the field to be infinite, and here field is infinite. M and R is there. So yeah, right. So why? So let's see. So if let's say V is a vector space over R or C, vector space over R, let's R. So what does that mean? Now, if I'll take the option 1 to be true, it means that V can be written as W1 union W2 union Wn. Okay, and all are proper. This is a proper, this is proper, this is proper. Everything is proper. Okay, sorry, yeah. This is proper and this is also proper. Everything is proper. Yeah, right, Mato. It is union but not the sum. And we know that W1 and W2 are the subspaces of V. Okay, then W1 union W2 is a subspace if and only if either of them is contained in other. So either W1 is contained in W2 or W2 is contained in W1. Okay, then only this is true. Right. So here what happened then? See, so if I can write V as a union of finitely many this, then what will happen? Since I know that this is a vector space, it means that this containment will be there, and hence I just get the largest space, say Wi. Okay, union will be some Wi, and since everything is proper, so this cannot be equals to W. Okay, and that proves that if you have any vector space over a infinite field, you cannot write this as the union of finitely many subspaces. Okay, is it clear? Yeah, Mato told the right thing that it is union, not the sum. Okay, so if it would have sum, of course you can write, but it's a union, so you cannot write, and it's not. It's like you can never write. So this is false. Never. Okay. Yeah. Okay, let's talk about the option 2. So I'll just erase here. Sorry. So that I can discuss here only. So option 2 is, of course, it's not difficult. Let's see. Let A be an element of MNR, then for any real number x and epsilon, there exists a real number y such that the determinant, oh, this is x plus epsilon. Yes, such that determinant of y I plus a is non-zero. Any matrix is either symmetric or skew symmetric, so we cannot write it as a union of any symmetric matrix. See, again, as uh, you see that Matho thing, comment. See, what you are saying, M and R is the is like is the sum of symmetric matrices and skew symmetric matrices. It's a sum, not the union. Why? Because see, if I take, let's say, just 1, 0, 1, 2. If I just take this matrix, this is neither symmetric nor skew symmetric, and hence it will neither be. So this will neither be in the symmetric and nor be in skew symmetric. Okay, and therefore this cannot be in the union. So this cannot be in the union. Okay, this cannot be in the union. See, it was not the sum, it was the union. Okay, union means if it is in the union, then it's either in one or two. But it's neither symmetric nor skew symmetric, so hence it cannot be here and it cannot be here. And therefore, you cannot write it as the union. Of course, you can write it as sum. You can break this as a symmetric and a skew symmetric matrix. Okay, right. Yeah, Sujata, R is an infinite field. Yes, right. R is an infinite field. Yes. So is it clear, Manmohan? Okay. So let's proceed now to the next option. So let A be an element of MNR. Then for any real number x and epsilon greater than 0, there exists a real number y in x minus epsilon and x plus epsilon such that the determinant is non-zero. Okay. So in the other way, what it is saying, see, if let's say lambda 1 dot 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 lambda n are the eigenvalues of A. These are eigenvalues of A. Okay. So one more, if it is clear, let me know. Not clear, then also please let me know. Yeah. So these are the eigenvalues of A, and so this implies, and let's say this is V1 dot dot Vn. These are the eigenvectors. So what are the eigenvalues of Ya plus A? So if I'll act on Vi, this is what? This is equal to Yivi plus Avi. Ivi is same as Vi. This is Vi plus Avi is lambda Vi or lambda Ivi. So this is equal to Y plus lambda I Vi. Okay. Okay. So it means that if lambda is an eigenvalue of A, then Y plus lambda is an eigenvalue of Yi plus A. Okay. And see, this is true because I is an identity matrix. This is not true in general. So this is, I'll emphasize it. If lambda and mu, I told in the last session also, this is an eigenvalue of A and this is an eigenvalue of B, then lambda plus mu need not be an eigenvalue of A plus B. So that's not true. Okay. But since here I is an identity matrix and we know that IV equals to V, and that is why this is true. Okay. So therefore, what are the eigenvalues of yi plus a? It's y plus lambda. So all the eigenvalues will be y plus lambda I. Okay. Okay. Fine. Now you read out the problem that for every element of MNR, there there exists a real number x and epsilon greater than 0 such that then for sorry, I'm sorry. Then for any real number x and epsilon, there exists a real number y such that determinant is non-zero. So determinant means non-zero means the product of y plus lambda I. This product is non-zero. So it means that every entry y plus lambda I is non-zero. So each entry I want to be non-zero. Yes, of course, corresponding to the same eigenvector that the sum will be same. But since we don't know the eigenvector, so that's why that is not true in general. So this is not true in general, I'm saying. This is not true in general. Okay, so you see that y, so you have x is any number and epsilon is any number positive. So x minus epsilon, x plus epsilon. Okay, and I need to find out y. Okay, so lambda 1, lambda 2, dot lambda n are there. So see, you have only n values and I have to find one y. So let's say lambda could be any here, anything. But I can just find one y here such that this is non-zero because I have infinitely many y's in between. I can take any y such that y plus lambda I is not zero. Okay, so I have to just discard n many values that y is not equals to minus lambda I. I just have to discard those values and hence this each of them will be non-zero and therefore the determinant of the matrix is non-zero. Okay, and hence I this statement is true. Okay, and in a nutshell, what this statement is telling, this statement in a nutshell is telling that the set of all invertible matrix GL and R is dense in MNR. It's set of all matrices. That means GL and R is dense in uh, yes, right. That is also right. That R eigenset value is dense in R, of course. But here it says that, like, given any A, that's like anything. I mean, it's a determinant zero, non-zero, anything. You can always find a sequence in GLNR which will go to the which will converge to A. So this we will see when we will read out the topology thing. Then we will see. But yeah, this big fact is not needed to solve this problem. This is easy. Just you have to analyze the eigenvalue. Okay. What about option 3 and 4? So option 3 is suppose A and B are two elements of MNR such that their characteristic polynomials are equal. And if A equals to C square for some C, then B equals to D square for some D. What do you think? This is correct? So what it says, let me you can read out and think in between. I am just erasing it. Okay. Yeah. So what do you think about option 3? So it says that if A equals to C square, then B equals to D square for some B. Provided that A and B have the same characteristic polynomial. Yeah, what do you think? Is this true or this is false? Yeah. So this is of course false. I'll just take A equals to 4, 4, 0, 0. Okay. And B equals to 4, 4, 0, 1. Okay. Now you can easily check, see, or you can just take 1, 1. Why to go 4, 4? Just take 1. It's easy to tackle. 1, 1, 1, 1. Okay. So option 3 is false, right? Because A is equals to A square, but B is not equals to D square for every D. And this you can check, it's not difficult to check. This option is false. Okay, right. What about the option 4? What about option 4? That for any subspace W of MNR, there exists a linear transformation T from MNR to MNR with W as its image. So I'll write just a theorem in linear algebra, which is very, very important, and that's very easy to prove. And you'll see that today only we'll be using that various time. So T from V to W. Okay. Let's not say. Let's say V and W are two vector spaces. Write the PPT in WhatsApp. Okay, since I'm erasing it here, so okay, at the end, whatever I remaining, I'll send you. But yeah, complex, then option 3 is true. I don't think so, because you see, even can you write this B as a square? Let's see if we can write B as a square. See, if, see A square equals to 0, so no, not A square, so A square. So if I can write B equals to D square, okay, or okay, yeah. So let's talk about let's take this option for an easier computation. I'll take. So yeah, Mato, I guess that's not true. So let's take this A 0 0. So A is this. Of course, A square A equals to A square again. Or no, this is right. And if I take B as 1 1 0 0, then if B square is equals to if B equals to some D square. Can you write this? It's like A, B, C, D, and a square is B. Okay. So can you write this B as a square of T? So Mato, why you told that if that's not true, of course. Even in the field of complex, if uh, I'm right, then that's not true. So Mato, why do you say that that's true? Any guess? Like, okay, fine. Okay, so this is not true even in the field of complex numbers. This is not true even in the field of complex number. Okay, yeah. Surya. So see, I'll send you whatever I have, but like since I'm erasing a lot of things, so I don't know whether it will be much helpful. But yeah, I'll say share this thing in WhatsApp. Okay, let's talk about the fourth option. Yeah, I was writing a theorem. So let's write down this. Okay, so if V and W are two vector spaces, yeah, but yes, diagonalizable matrix. But of course, if it is diagonalizable, then of course, since every element has a square in complex, then that's true. But right, V and W are vector spaces, and let's say if I fix a basis for V, okay, V1, V2, Vn. Okay, if this is a basis for V and B, and if I'll take any B tilde, W1, W2, Wn, any W1 to W1, I'm not telling this is a basis of V. And this may or may not be a basis. May not basis. Okay, of W. And if I define T from Vi to, okay, so this will give me a linear transformation. Okay, with sense Vi to Wi. Okay, this will be a linear transformation. Okay, so now here, what is the problem? If for any space subspace W of an MNR, there exists a linear transformation T with W as its image. Okay, so what I will do, I'll take, so it's MNR, so I'll take my a base is B of MNR as just usual Eij. Okay, Ij from N1 to N. Yeah, this T is unique, right? You are right. This is unique. Yeah. So if B, I'll just take a basis and I'll take a basis for W, W1 to WN. Okay. And now what I will define T, I'll define T as, let's say, or let's write down E1 N square thing. I don't want to, I equals to 1 to N square. Okay. I just define TEI equals to WI if I is less than equals to L, and rest of the things equals to 0 if J or I if I is greater than L. Okay, if I define this, that T of E1 W1 E2 W2 EL WL and rest of the things is 0, so then what is the image of T? By definition, the image of T is, so the image of T is equals to W. Okay? Yeah. So this option is true, that for every subspace W of MNR, I can find a linear transformation T from MNR to MNR with W at its image. Okay, so this is one I gave you. Okay, okay. So I hope this is clear. So let's proceed to the next problem. So what was the correct options? 1 and 4. Oh no, sorry, 2 and 4. 2 and 4. Option D. Okay, I'll repeat option D. Option D. See, what is the option D? It says that for every W subspace of MNR, there exists a linear transformation T such that image of T equals to W. This was the option D. Okay. What I told, I'll take a basis. I'll take a basis of MNR is equals to E1, E2, En square. Okay. This is a basis. I'll take a basis of W. Okay, W is a subspace of MNR, so it must have a basis W1 to WL. Okay, now I'm defining T as T from MNR to MNR as you send T of T of EI, because every linear transformation is uniquely determined by the action on its basis. So if I define where does T sends to E1, E2, En square, I'm done. So I'll just see T of EI equals to Wi if I is less than equals to L and 0 if I is bigger than L. Okay, then T is a linear transformation and the image of T is equals to W. Is it clear, Sujata? So I found, so the problem was to find a linear transformation T whose image is W. So I found a linear transformation T whose image is W, and therefore this option is correct. So Sujata, this is clear. Okay, thank you. So let's proceed to the next problem. Yeah. So for a positive integer n, let A be an n cross n matrix with entries in R such that A to the power n square has rank 0. Okay, so rank of this is 0. But rank 0 means what? When can the matrix has rank 0? It means that matrix itself has to be 0, because then only 0 rank is possible. So it means that A to the power n square is 0. Okay. Okay. And let GON denote the n cross n matrix with all entries equals to 0. Which of the following statements are true? Which of the following statements are equivalent to the statement that A has n linearly independent eigenvectors? Okay. So A has n linearly independent eigenvectors, n linearly independent eigenvectors, if and only if A is diagonalizable. Okay? Yes, A is diagonalizable. Okay. So see, the let's analyze a n square is 0. So a to the power n square is 0. Right, option 3 is correct. Option 3 is of course correct because A is a 0 matrix, so that's a diagonalizable. And now a to the power n square is 0. So this implies that a to the power n is also 0. Because why? Because a to the power n square is 0 and n square is bigger than n. So a to the power n has to be 0. So this implies that so all the eigenvalues are basically 0. Eigenvalues are 0. Okay, so A is nilpotent. A is nilpotent. Okay, and you see this option is nilpotent, this is nilpotent, and this is nilpotent. So let us prove that nilpotent matrix cannot be diagonalizable. A non-zero nilpotent matrix. So if A is not equal to 0 and A is nilpotent, then A is not diagonalizable. A is not diagonalizable. Okay, yeah. So let's see. So this is very easy. See, if A is diagonalizable, what will happen? It means that I can write A as P D P inverse for some P invertible and D as diagonal. Okay, and since A has all the eigenvalues at 0, so D will be what? It's 0, 0, 0. Okay, fine. So now what is given? That A to the power n is 0. So A to the power n equals to P to the power n, sorry, P D to the power n, P inverse. But like, oh, I don't need to do that also. So from here, what can you say? D, all the diagonal entries are 0. So what does mean? That means A equals to 0 from here. Okay? And so, and therefore, but A we have, yeah, but A we have already assumed that A is non-zero. So that's not possible. That's a contradiction. And therefore, a nilpotent matrix cannot be diagonalizable. Okay? And hence, these all options are false. So option, this is the only correct option. Okay? Yeah, let's proceed to the next problem. I hope this is clear. Yeah. Okay. So yeah. So this problem is again like solely I will use the theorem that I told that if V and W are two vector spaces and take a basis of V and choose any n elements of W. So if V1, V2, Vn is there and any n elements W1, W2, Wn, then there exists a unique linear transformation T which sends Vi to Wi. Okay, this is the thing that I'll be using in this problem. Okay, so let's do this problem. Okay, so U and V are given. U as 2x plus 3y plus 4z equals to 0 and V as x plus 2y plus 5z equals to 0. So let's write down the basis of U and V so that it will be easier to analyze. So let's write, I'll erase this, and 2x plus 3y plus 4z equals to 0. This implies 2x equals to minus 3y minus 4z. Okay, so x equals to minus 3y by 2 minus 4z by 2. So I'll just take as of course I can take anything, but let's take if I take y to be 3, y to be 2, then this will be minus 3, 0. And if I take z to be 2, then this is minus 4, 0. Yeah. Oh, sorry. This will be in the third. Yeah. 0, 2. Okay. Right. So this is a basis. So a basis will be I'll name it as U1 and U2. Okay. So this. Similarly, V has X equals to minus 2y minus 5z. So I'll take minus 2, 1, 0 and minus 5, 0, 1. Okay. So again, this I'll name it V1 and V2. Okay. So U and V both are two-dimensional thing. So U I'm writing as this is U1 and this is my U2, this is my V1, this is my V2. I wrote down U1, U2, V1, V2. Okay. Now what is the first option? There exists an invertible linear transformation T which sends U to V. Okay. Such that T of U equals to V. Okay. And it is an invertible linear transformation. Okay. What I will do? Again, as I told, I will just use the theorem that I have just stated. So what I will do, I'll send T of U1 equals to V1, T of U2 equals to V2, and note that V1 and V2 are linearly independent. And now, if I want T to be invertible, I will take something which is, and here I need a basis, okay? And since T is from R3 and U1 and U2 are two vectors, so I can always choose a third vector. I just write U3, okay? T of U3, which is not in the span of U1, U2, and write V3, which is not in the span of V1, V2, okay? So U3 is not in the span of U1, U2, and V3 is not in the span of V1, V2. Okay, and see, U1, U2, U3 all are linearly independent. V1, V2, V3 all are linearly independent. It means that T is invertible and T of U equals to V. Okay, so this option is correct. And therefore, the option 2 is false because it just says the negation of 1. That there does not exist any invertible linear transformation such that TB equals to U. Okay, so is this clear? The option 1 and 2. So we can proceed to option 3 and 4. Okay, okay. So let's proceed to option 3. So option 3 is what? That there exists a linear transformation from R3 to R3 such that T of U intersection V is non-zero and the characteristic polynomial of T is not the product of linear polynomials with real coefficient. Okay. So it means that all the eigenvalues of T should not be distinct. Okay, because if all the eigenvalues of T will be distinct, then I can write the characteristic polynomial as the linear factors. Okay, so sorry, yeah, let's write down this. So T of U, I want this to be, I want this intersection V is not equals to 0. So it means that it has to be more than 0. And the second thing is the characteristic polynomial of T should not be linear. So it should not be linear. So that's right, not linear. Not linear, like linear products. Okay, not linear, not linear product. Okay. No, we cannot take V3 anything. Why? Because if you take V3 anything, then it won't be invertible. We want invertible here. Okay. So for example, if you take T of U3 here to be 0, then you see that U3 is in the kernel. And so the kernel is non-trivial. And therefore, this is not invertible. So since we want an invertible operator, we will take V3 to be independent of V1, V2. Okay. So since we need an invertible, that's why we cannot choose V3 anything. Okay. But okay, for the invertible, right? So let's write. So again, T of U intersection V is non-zero. What I will do, I'll just take T of U1 equals to V1. So see, now T of U1 equals to V1, it means that T of U intersection V at least contain the span of V1 because V1 is there. So this is satisfied. Okay. Now I want the second to also be satisfied. What I will do? I'll just take T of U2 equals to U2 and T of U3, sorry, is also U3. Okay, so you see that this, so this choice shows that T of U intersection V is not 0, and these two options shows that one is eigenvalue with U2 and U3. U3 I just chose not linearly independent of U1 and U2. Okay, so this satisfies these two things, and hence this option is also correct. This option is also correct. Okay, so any doubt? Otherwise, let's proceed to the option 4. Okay, so option 4, what it says? That there exists a linear transformation T from R3 to R3 such that T of U equals to V and the characteristic polynomial of T vanishes at 1. Okay, I'll repeat C. Okay, let's repeat C. So let's repeat C option. See, what is the option that is required? That it says that construct T such that T of U intersection V, intersection V is not 0, and the characteristic polynomial of T should not be equals to like x minus lambda 1, x minus lambda 2, x minus lambda 3, where lambda 1 not equals to lambda 2 not equals to lambda 3. We don't want this. This should not be. Okay. See, this is what it says. That there exists a linear transformation T from R3 to R3 such that T of U intersection V is non-zero. That's the first thing. And the second thing, the characteristic polynomial of T is not the product of linear polynomials with real coefficients. Okay. So yeah, so of course I can just write here some linear. Okay. Okay, so I don't want T to be split in the linear factors. Okay. So what I will do, I'll take, see, U1, U2 was the basis already. I'll just take U3 to form a basis of R3. Okay, this is a basis of R3. Now, the first requirement asks you that T of U intersection V has to be non-zero. So, what I will do, I'll take T of U1 equals to V1. Recall that V1, V2 were the basis of V. Okay, so this. So what this implies? This implies says that V1 is in the T of U. Okay, so this is satisfied that this is not 0. Okay, now let's satisfy the next two things. Next two things says that characteristic polynomials should not split. It means that all the eigenvalues should not be same. What I will do, I will just take TU2 equals to U2. So what is the eigenvalue here? This implies 1 is an eigenvalue, and T of U3 equals to U3. This implies 1 is an eigenvalue. This implies when I will write the characteristic polynomial, so if I write the characteristic polynomial of T, so that will be something times x minus 1 square. Okay, this something will be determined by what is the other eigenvalue, third eigenvalue. Okay, but this will be there because 1 is an eigenvalue, 1 is an eigenvalue, and U2 and U3 were linearly independent, so that's why these two eigenvalues are different. This means you took 1 is not 1 is 2, so not linear. No, I'm not getting what you're saying. You took m of 1 is 2. No, see, T of U2 is what? T of U2 is U2. As I told in the theorem that if you have a basis U1, U2, U3, and if you choose any three vectors V1, V2, V3, then T of U1 equals to V1, T of U2 equals to V2, and T of U3 equals to V3. This determines a linear transformation, and that linear transformation is unique. What I choose here, I choose U1, U2, U3, and V1, sorry, V1, U2, U2, U3. Okay. Algebraic multiplicity of 1 is 2. Right. Right. You are right. So therefore, this T and this sends to this sends to this, and this sends to this. Okay. And this satisfies this property. And this option is correct. Okay, let's talk about the option 4. That is again similar. Okay, there exists a linear transformation T from R3 to R3 such that T of U is equals to V and the characteristic polynomial of T vanishes at 1. So now what I want? 1 has to be an eigenvalue. Okay, this is what we want. Okay, so what I will do for the fourth option, I'll just take T of U1 equals to V1, T of U2 equals to V2. These two options will give me this, that T of U equals to V. And the third option, I'll just take U3 equals to U3. Then this option will give me 1 is a eigenvalue, 1 is an eigenvalue, and hence it will vanish at 1. And therefore this T will work for option 4. Okay, so is this clear to everyone? Okay, so I hope it is clear. And see, this theorem is very important, a very powerful theorem, where I have written this. Forgot where I have written. So it's like this, that if U and V are two vector spaces, you take a basis of U. See, this is very important. You are taking a basis of U, and I am taking any n. So if the dimension of U is equals to n, so any n vectors here. Okay. Any and it could be linearly dependent, independent, or everything to be zero, anything. I don't care. Okay. Then T of U1 sending to W1 will determine a unique linear transformation. Okay. This property is very important theorem. Okay. So I hope this is clear. Okay. Okay. So now I guess three problems are left. So let's take a break of 3 to 4 minutes, and then we will discuss the rest of the three problems. Okay. And in the meanwhile, if you have any problem, you can ask, and we will be discussing the doubts. Okay. Yeah. And one suggestion, again, one suggestion. So, see, you can use the WhatsApp group for discussion among yourself. Okay. So, see, that's a WhatsApp group. Around, I guess, 100 people are there. So, what you can do, you can just discuss among yourself. Okay. Just like if you stuck somewhere, just ask somebody, like, I have stuck it here, can you help? If somebody knows, like, please help him or her. In this way, what will happen? You all will like be prepared for the examination simultaneously. Okay. So and you will learn more in that way. Okay. So that is a suggestion. You can follow that. Yeah, of course, I'll not be able to reply on that because I'll not be free all the times. So, but you can discuss among yourselves. Okay. Okay. So, any doubt, then we can discuss, or we will wait for a couple of minutes. You can have your water, tea, coffee, anything. And I guess three problems are remaining, or four, 12, 13. Yeah, last. No, 14, four problems. Okay. Okay. So I have solved problems till 10. So let's see the rest of the four problems. So you all can help me to solve the remaining four problems. Okay. So yeah, so we can resume in 1 minute. Okay. Yeah, okay. So let's start. So yeah, let V be the vector space of polynomials f of xy in Rxy. So it's a polynomial in two variables. Okay, with total degree less than 3. Okay, so it means that f of xy is like, how can we write f of xy? It's like a 0 x square, or let's say 2 0, so that x square plus a 1 xy plus a 2 y square plus a 10 x plus a 1 y plus a 0. Okay, so this is an arbitrary polynomial in Rxy where all these a I j is in real number, and which has degree less than 3. Degree is 2. Okay, fine. So what is the basis for this? So basis we can write, of course. A basis will be like what? X square, xy, y square, x, y, and 1. Okay. So it's like x square, xy, y square, x, y, and 1. So what is the dimension of this? Dimension equals to dimension of V equals to 6. Okay. Now let's see the linear transformation from V to V. So T from V to V. And it sends f to its partial derivative with respect to x. Okay. So let's write down the matrix of T. It will be like all will be very easy to determine. Okay. So let's see. So see, when will T be 0? So T will be 0 if if the function will only be the variable of y. If there is no x, then it will be 0. So let's write T of x square is what? 2x. T of xy is what? Sorry, not sorry, it's y, because we are taking x derivative. T of y square is 0. T of x is 1. T of y is 0. T of 1 is 0. Okay. So what is the matrix of T? Of course, we can write. It's not difficult. But like, see, the 3 linearly independence goes to 0. Y square, y, and 1. Y square, y, and 1. These 3 linearly independents are going to 0, and 3 linearly independents are going to non-zero. And therefore, the nullity of T will be 3, and the rank of T will be 3. Okay. But of okay, this is clear. But yeah, we can write down the matrix also. So matrix will be what? So I'm writing with respect to this basis. So the basis is important. So it's like 0 0 0 2 0 0 0 0 0 0 1 0, and then 0 0 0 0 0 0 0 0 0 0 0 1, and then 0 0. Okay. So, as I told already here, that the null space of T will be generated by x, x square, sorry, it will be generated by y, y square, and 1, and the range space of T will be generated by x square, xy, and x. Okay. So the dimension is 3, rank is 3, and sorry, the nullity is 3, rank is 3. So nullity of T is at least 3. It means that at least means less than equals to 3. Of course, that is true. The rank of T is at least 4. That's false. Rank of T is at least 3. That's right. T is invertible. Not true, because nullity is there. So T cannot be invertible. Okay. This was an easy problem. Let's go to the next problem. Yeah. Let W be the space of C linear combination of the following functions. So you have 4 functions: f1, f2, f3, f4. Sine z, cosine z, sine 2z, cosine 2z. And let T be the linear operator from W on W. So T from W to W. And it is given by f goes to F prime. Okay, it's a complex differentiation. Then which of the following statements are true? Okay, right. So what do you think about this problem? Any guesses? Yeah, any guess? Okay, okay. So let's try. Okay, let's try this. So see, F1, F2, F3, F4 all are linearly independent. Okay, so basically this sine nz and cosine nz such that n is in n. These are all linearly independent things. Okay, so this means all these are linearly independent. Okay, so let's write down what is F. So let's write down the matrix of T. So let's write T of sine z is what? It is cosine z. T of cosine z is what? Minus sine z. T of T of sine 2z is what? 2 times cosine 2z, and T of cosine 2z is what? Minus 2 times sine 2z. Okay. So what will be the the matrix corresponding to T? It will be, first is cosine z. So 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 0, 2, and 0, 0, 0, minus 2, 0. Okay. This is the T. So this is the block diagram. This is a block diagonal matrix. See, this is one block, and this is another block. Okay. So, so dimension of W is 3. That's wrong because as I told, these all are linearly independent. So dimension of W is 4. Okay. And now we have to determine the Jordan blocks. Okay. So let's find out what are the eigenvalues of T. So what are the eigenvalues of T? It's a block thing. So eigenvalues will be the eigenvalue of each block. So what is the eigenvalue of this matrix? So eigenvalues of this is what? What is the characteristic polynomial? If you write down the characteristic polynomial, what is that? It's x square, trace is 0, determinant is 1, so x square plus 1. And this 0, 2, 2, 0, this will be x square plus 4. Okay. So what are the roots? Since we are in the complex thing, so this will have the roots, so plus minus iota and plus minus 4 iota. And therefore, if I'll write T as a Jordan thing, since this has four different, sorry, plus minus 2, I'm right, wrong, plus minus 2 iota. So the corresponding, the Jordan block or the Jordan matrix will be I minus I, 2I, and minus 2I. Okay. So this has single block is there. Okay. Okay. So therefore T has 2 Jordan blocks, false. T has 4 Jordan blocks is correct. The span of F1 and F2 is a Jordan block of T. That's not true because span of F1 is this and the span of F2 is this. So I don't know what does this mean. Like, see, if the meaning of this is the span of F1 is a block and the span of F2 is a block, then it is true because span of F1 is a block, span of F2 is again a block. But if it is asking a span of F1, F2, then that's not a Jordan block. Okay. So 2i and minus 2i. 2i. Oh, okay. So that's earlier comment, right? Yeah. So hence, so see, as I told, so I don't know what is the meaning of this. So span of F1 and F2. So I guess that's meaning of span of F1, F2. is a Jordan block of T. That's not correct. So this is false. So the correct option is fourth. I don't know what is the answer key. So as I told, I don't know after 11th what was the answer. So, but yeah, the right option will be fourth one. Okay, so is there any doubt, or we can proceed to the next problem? Okay, so let's proceed to the next problem. Yeah. Okay. So if you any doubt, you can stop me. Now there are two problems left, 13 and 14. Okay, so let's see the 13 problem, number 13. So let Pn be the vector space of real polynomials with degree at most n. Okay, and let this be an inner product on Pn with respect to this. Okay, uh, to which, oh sorry, with respect to which is an orthonormal basis of Pn. So let f is this. So it means that this is an orthonormal basis with respect to this inner product. It means that if I take anything x to the power k by k factorial and x to the power l by l factorial, that's 0. Okay, so this is given. This is equals to 0. Okay. Now f is this and g is this. So we have to see inner product of fg will be what? Okay, so let's see what is the inner product of fg. So if I'll write fg, see what is this that we know? We know this is an orthonormal basis. So what we know that x to the power k by k factorial times x to the power l by l factorial. So let's write down. Okay, so let's write down here again. Yeah. So what we know here, x to the power k by k factorial, x to the power l by l factorial, this is equals to, what I can do, I can take this k factorial out because this is an inner product and hence I can take the constant out. So 1 by k factorial times l factorial and it's x to the power k and x to the power l. Okay, and this is equals to 1 by k factorial times l factorial delta, and what we know that this will be that this is an orthonormal basis, so either it's 0 or it's either 0 or it's a 1. So this thing will be, this is final, that this is equals to either 0 or 1 depending k not equals to l or k equals to l. Okay, fine. So let's see. So now you see that f is what? Summation alpha I xi and g is beta I xi. So let's find out what is fg. Fg is what? Alpha I x to the power I and this is beta I x to the power I. Okay. So this I can write. What I can write this? Summation alpha I can take out and this will be x to the power I, and beta I again I can take out, so that's beta I and I equals to 1 to n and x to the power I. Okay, and what I know here from the first thing, I know that x to the power I by I factorial and x to the power I by I factorial is equals to 1. This is what I know. So it means that what this gives me, x to the power I and x to the power I will be what? It will be, I can, this is a constant out, so this is an I factorial square. Okay, so this is what? This is summation alpha I beta I and I factorial square. Okay, so what is the value of fg? That's this. Is this clear to everyone? So hence the correct option is fourth. And of course 1, 2 are not correct. You can check. And this is indeed a unique inner product. Okay, because I haven't used anything. I just determined the value and this is coming this. Okay, so this is a unique inner product. So this is also false. Okay, Is this clear to everyone? Yeah. So yeah, so you can respond yes or no, so that I can proceed to the last problem if it is clear. Yeah, it is unique. Why? See, as I told, see, what is the inner product of FG? So I haven't used anything. See, what is the inner product of FG? The inner product of FG is by choice is like, see, it's like summation alpha I x to the power I, summation beta I x to the power I. Okay. I am not using anything. Maybe some other inner product with respect to which it's a, which that basis is orthonormal. Whatever that is, right? Yes, it can be, but I'm writing the inner product. See, I'm not using anything. I'm just using the properties of the inner product. Let's see. So the first property I'm using, that I can take the constant out. So I took out the constant alpha I and beta I. Inner product x to the power I and x to the power I. Okay, fine. Now this is, and so what I know from that, if this is some other inner product, then what I know that x to the power I by I factorial. So let's write. So what I know is x to the power I by I factorial and x to the power I by I factorial. Whatever inner product it is, I know that this is 1 because this is the, with respect to inner product, this is an orthonormal basis. So I know that this is equals to 1. Whatever this inner product is, whatever it is, I don't care. But this is equals to 1 because, or let's name this is 1. Okay. And this is 1, with respect to 1, we are finding out. Okay. Or not write 1, 1 is already there. Or let's write some, right. Let's say, what should I write? Let's write something 0, 0, 0. Okay. So now I'll again use the inner product property. Since this is an inner product, I can take the constant out. So I'll take 1 by I factorial out and 1 by I factorial out. This is a square. So this is x to the power I and x to the power I, and this is equals to 1. And this implies x to the power I and x to the power I equals to I to the factorial square. And therefore this is equals to alpha I beta I factorial square. And this gives you the unique, this is the unique inner product. Is it clear, Manmohan? Okay. Yeah. So I have the, so this is 0, this is 0. Yeah. I haven't used anything. Okay. Yeah. Fine. Thank you. So let's discuss the last problem. On the complex vector space C to 100 with a standard basis this, consider the bilinear form Bxy, which is defined as summation xi yi, where xi and yi are the coefficients of ei in x and y. Okay, fine. So it means that x is equals to x1 dot 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 x to the x 100 and y is equals to y1 y 100. Okay, and then which of the following statement are true? So we have to talk about the degeneracy, non-degenerate, 0, 0. Okay, so let's see. So first of all, what is, if B from V cross V to C is non-degenerate? What do I mean by that? It means that, so B is non-degenerate. This means that if for every W in V, V of VW equals to 0, this implies B equals to 0. Okay. This is the definition of a non-degenerate bilinear form. That if B of VW is equal to 0 for every W, then V has to be 0. Okay. And equivalently, one can show that if I write down the matrix of B, but what is the matrix of B? Okay. So let's write down first the matrix of B. So the matrix of B is equals to, okay. So this matrix will depend on the choice of the basis. So what I will do, I'll write B of E1 E1, B of E1 E2, dot B of E1 En, and the ijth entry will be B of E1 Ei Ej. Okay, so this is the ijth entry. So we say that B is a non-degenerate bilinear form if the determinant of B is non-zero. Okay, so we say that B is a non-degenerate bilinear form if the determinant of the corresponding matrix will be non-zero. Okay, so let's write down the matrix of B. What is B? So see what are the bases? Basis is EI, standard basis. So what we know that if I take B of EIJ, what is this? This will be delta IJ. That means 1 if I not equals to I equals to J, and 0 if I not equals to J. Okay? And therefore, this is 1 in the diagonal and 0 otherwise. Okay? Now you see that you have the B. So what is the determinant of B? So determinant of B is 1, non-zero, and hence B is non-degenerate. Okay, fine. Okay, so this means this option is correct. Okay. Now the second option is restriction of B to all non-zero subspaces non-degenerate. Okay, so now see, now B is non-degenerate. Now it is asking that if I restrict B to some subspace of V, then also it is non-degenerate. So let's see. Sorry, what happened? Why it came again? Space to trace. Yeah. Yeah, let's add a new page. Yes, okay. So what it says that if I restrict B on this, then also B is non-degenerate. Okay, this is what it says that. Okay, so, but this is not true. This is not true. Why? See, what is B? B of xy is what? It is given as x1, y1 plus x2, y2 plus x100, y100. Okay, this 100 is just a number. So, of course, this is, you can take 4, 10, okay, anything. Okay, but let's see this. I'll take W as the span of, let's take 1i 0 0 0 and 0 0 1i 0 0 0. Okay, if I take W as this, what is, so this is my W1 and this is my W2. What is B of W1? W1 to W1, of course. What is this? This is 1 times 1 plus I times I plus 0. So that's what? 0. And what is B of W2 W2? This again 0 by the same logic. And B of W1 W2 is 0. And therefore, B is itself 0. So therefore, B is itself 0 when we restrict on W cross W. And therefore, B cannot be non-degenerate. Okay? So B cannot be non-degenerate. Okay? So is it clear? Is it clear to everyone? Just respond. Yeah. Okay, so I hope it is clear. Let's see the other two options. If it is not clear, you can let me know. Yeah, so this option is wrong. This is not true. Okay, thanks, Aviru. The third is there is a 51 dimensional subspace W of C100 such that the restriction is a zero map And there is a 49 dimensional subspace of W such that the restriction is a zero map. Okay. Okay, right. But see, with the choice that I just gave with this, can you see at least that can you say that at least one of this is true? Which option? See, the choice that I just now I choose some basis for W. So can you similarly choose a 49 dimensional subspace W such that B is zero? With the similar, like just now I choose. D is true, right? D is true. So how would I choose? So I just take W at what I will do. I'll take 1 I and then 0 0 and 0 0 1 I 0 0 and 0 0 0 0 1 I 0 0. In this way, so this since I'm choosing two at a time, two at a time. So at most, how many I can choose? I can choose 50. Okay. So I can choose 50. Okay. This 50 will be linearly independent. What I will do, I'll just take any of this 49. Okay. So I'll just take W to be any of this 49. I can choose 50, but I will just take any of this 49. Okay. And then B restricted to W cross W is 0. Okay. And hence B is a linear B restricted to W cross W is 0 and hence B is 0 when you restrict on W cross W. Okay, this is clear. Let's see what about option C. So option C or option 3 says that there is a 51 dimensional subspace such that the restriction of B is a zero map. Okay, that's also easy. So suppose if there exists a W dimension W is 51 such that B restricted to W cross W is 0. 0. Okay. So, see, with the fourth option implies that there exists a basis W, or let's write, or there exists a subspace W tilde, dimension of W tilde is 49, such that B restricted to W tilde cross W tilde is 0. Okay. So now with the assumption, I am assuming that there exists W such that B of W cross W is 0, and with the fourth option I know this. Okay. So see, so I am considering W intersection W bar tilde. So this dimension of this will be at least one, okay, because the dimension of W plus dimension of W tilde is 101. So the one has to be reduced. Okay, so that's why it is has to be at least one. Okay, so 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 take take, let's say V is in the intersection. Take V is in the intersection W tilde. So V will look like how? So V has V11, V12, dot dot dot, V100. Okay, or not one is also needed, just V1 to V100. Let's write V1, V2, V100. How is it 101? Isn't it 100? No, that's why. See, dimension of, see, what is dimension of W plus W tilde? This is equals to dimension of W plus dimension of W tilde minus dimension of intersection. So this is 100 and this is 49 plus 51 minus dimension of this. Okay. So this means what? This is 101. So this has to be 1. I'm saying. Okay. The intersection has to be 1. Okay. So this has to be 1. Okay. Right. Is it clear, Manmohan? 49. Oh, 49 plus 51 is 100. Oh, right, right. Oh, sorry. Oh, that's my mistake. Sorry, sorry. Okay, okay. No, no, no. Yeah, that's my mistake. Sorry, sorry. Yeah, that's a silly mistake. Okay. Yeah, then what is the question? Then I have to see. Okay. Okay, so there is like, okay, so, mm, right. Okay, fine. So what I will do, I'll not choose this 50, but right, right. What I will do, see, from the previous thing, I know that there exists a W, such that dimension of W is 50 and B restricted to W cross W is 0. Okay. This we know because as I told, I can see, as I told here, where it went. Yeah, as I told that I can choose this to be 50, but since 49 is required, I'm choosing 49. Okay, so I can always choose 50. Okay, oh, that's my mistake. Yeah, so now what I will do, dimension of again W intersection W tilde, this is equals to 1. Okay, right, Manmohan? That now I have not chosen the 49th dimension, I have chosen the 50th dimension W. So the dimension of W is 50. So now the intersection dimension is 1. Okay, and therefore, so let's V is in the W intersection W tilde. Okay, so V I am writing as V1, V2, V, let's take 100. Okay, now see, V is in this, so what I will do, I'll just take V1 minus V2, I'll just take one of them is minus. Okay, and rest of them is fixed. So this V is of course, this is my W. So V and W are linearly independent. Okay, these are linearly independent. Okay, so it means that if I combine the basis of W, W tilde and union this W, then what is the dimension of this? The whole dimension will be equals to 101. Okay, because I have, see, or let me write down like this. What is the, so I have V, W, dimension of W is 50, dimension of W tilde is, what is my W tilde? Oh, W tilde is 50, sorry. Okay, so yeah, so W is 51. Yeah, so there might be this, let's say, there might be that numbering. W is 50th dimension and W tilde is 51 dimension and W intersection W tilde is 1 dimension. I choose a basis here in W intersection W tilde. V equals to V1 to V100. Okay, so there is, of course, since the basis, so there is some non-zero element. So assume B1 or B2, anything is non-zero. So I am writing W as minus B1 and V2 and rest of them is V100. Okay, and now V and W I got. Clearly V is linearly independent to W. V and W are linearly independent. So now I am saying that V and W are linearly independent. So what I will do, I'll just consider W, W tilde, and this singleton W. Okay. So this combinedly, since W cannot be in this, it cannot be in this. Okay. And hence, what is the, like I am getting one extra vector. Okay. And that will contradict that the dimension of V is 100. Okay. Is it clear, everyone? So I found a W which combined with the or W is misleading. So let's write some V tilde. Okay. So I found some V tilde which gives combinedly with W and W tilde gives the dimension to be more than 100. And that's a contradiction because the dimension of the vector space is 100. Okay, is it clear to everyone that you cannot find a 49, a 51 dimensional subspace? Yeah, please let me know if it is fine. Okay. Yeah. Okay, Marisa. So I guess it is fine for everyone. And this was the last problem. So if you have any doubt, we can proceed or we can end the session. So just let me know if you have any doubt. Yeah. And the next session will be on the next session will be on Saturday, the upcoming Saturday. Is it what date? I don't know. And Sunday. And I'll be discussing the real analysis problem. Okay. So yeah, so any problem, then you can ask or we can stop the session. So how was the session today? Like was it okay or I have to pace the down? Because last time I got some message that the pace was fast. So that's why I reduced the pace this time. So yeah. So you can say how was the pace? Like was it okay or we have to reduce the pace? See, bilinear form, I guess, see, even in the Hoffman Kunje you can read. Oh, because I guess Hoffman Kunje cover bilinear form because if I remember, yeah, but of course, Hoffman Kunje has bilinear form. I don't remember whether Kumarasam has the bilinear form. This I don't remember, but yeah, Hoffman Kunje, of course, and this will be a nice book. So yeah, you can look at Hoffman Kunje. Yes, okay. Yeah. So in the from next session onward, like try to solve the problems beforehand so that like we can it's like a kind of discussion session, okay? So that you can say because I see I might not get time to solve all the problems. So that's why I'm saying, okay? Yeah, so okay, so we can then stop here and thank you for your time and we'll meet again on Saturday, next Saturday. Okay. Okay. Goodbye. Take care and solve as much problems as you can. Okay. Take care.